So continuing on with our trig unit, we are going to take a look today at trig functions and what happens when we combine them or put a factor in front of them or square them or different things of that nature. Okay. One thing that we have noticed when we've been dealing with trig functions is this idea of a period, meaning how long it's going to take to see a graph repeat itself. So this word periodicity, meaning like what's the period of your function. So we're going to take a look at this first section. It says when a trig function is combined with a polynomial, the resulting function may or may not be periodic, meaning it may have a repeated pattern or it may not. So these first four examples I have graphed out for you, and we're going to take a look. This first example that we have here is the sine of x plus x squared, and it's a pretty graph, but it is not a periodic graph, meaning it doesn't repeat itself. It looks more like a parabola. Notice that factor is that x squared added onto it. But I would have to say that this is not a periodic function. Now look at your second graph. Again, very pretty graph, but again, not periodic. It doesn't, when we're thinking periodic, we want to think like sine or cosine has that repeated pattern. There is no repeated pattern here. I could say it is symmetric to the origin, or I could say it's an odd graph, meaning it would be the same thing right side up and upside down, but not periodic. Third graph, now we got a periodic graph. I can see it has a repeated pattern over a certain amount of time. It has a constant pattern, so this is definitely going to be a periodic function. And our last one, now, maybe looks periodic because again I have that curve. However, this one not periodic. It doesn't have a constant repeated graph. As I get closer to the origin, I can see that the distance between the curves or the waves gets larger, and the further away from the origin I get, the distance gets smaller. So it looks like maybe periodic because maybe it's following that sine and cosine curve, but it's not a consistent repeated pattern. So periodicity, we kind of want to think, I want a repeated pattern. Okay. Now, when we move on, a sinusoid, when it's added to a non-constant linear function, the result is not periodic. And we saw that up in letter A, right? So we had something that was added to a function that was not periodic. And actually in letter A, it wasn't even linear, it was a quadratic. However, the same thing's going to happen when it's linear. The graph repeats its shape at regular intervals, however, it takes on different values. So I'm going to see it's basically like a sine or a cosine curve, but tilted. So for instance, number 2 says the graph of this function, and notice here's that linear factor that they were talking about. Oscillates between two parallel lines. It says, what are the equations of the two lines? So if we look at that graph, again, here's that idea. It's almost like a sine curve, but tilted. And I can see that there's got to be two lines that it's kind of wiggling in between. So when we do this, things that we want to take note of is the amplitude. All right, so if I'm looking at the amplitude for my sine function, amplitude's that value in front of the sine itself, I could say the amplitude on this is 1, meaning the height of the wave is going to be increasing up 1 or decreasing down 1. Okay. The other thing I want to think about is that linear part of the equation. So the linear part, like we had highlighted before, is that 0.5x. So what is that telling me? So that's telling you that's that function. That's going to be that change of the graph. That's going to be that tilt of the graph. However, what I have to do is think, but the amplitude of the function being 1, meaning it has to change it by 1. So if maybe if we were to put this into words, I could say sine of x is going to oscillate, okay, between -1 and 1. That's coming from the amplitude. So if I'm thinking of that linear function, so that whole idea of that 0.5x part of that function will be I can think up, because it has to go up that positive one. So I can say up at y equals 0.5x plus 1. Okay. And it's also going to go down. Same equation. So we have that 0.5x, but I'm going down the amount of the amplitude. Okay. Maybe just to give you another example here. Not graphed out, but I'll give you another example, just so you can maybe kind of see what's going on. So let's say we had 4 cosine x plus 2x minus 1. So if we did this same idea, identifying that linear function. So here's that linear function. Other same idea, identifying the amplitude. So how would I find the lines that it oscillates in between? All right, so I would take that linear part of the graph thinking add on the amplitude because it's going to go up that amount. Or I could take that graph and subtract the amplitude. Okay, giving us the actual lines that it's going to oscillate between. If we were to simplify these, this would give me 2x plus 3. And over here, this would give me 2x minus 5. Right. So if we go back to that first equation that we had over here, this 0.5x plus sine of x, just to show you what happens, if I were to graph out the functions that we found, so we found 0.5x plus 1, I can see that it's going to keep touching that graph. And if I were to graph out the other one of 0.5x minus 1, again, I can see that that's on the bottom. Okay, so that whole idea is find that linear function, find the amplitude. You want to think add and subtract the amplitude to find where those functions are going to be. Okay, so what happens when we have sums and differences of sinusoids? Okay, so sinusoids being like sines and cosines. And when we have those, different things happen when you add or you subtract them. And you can see this in the real world with things like sound waves, voltage in electrical currents, airflow, and sometimes they interact when we put them example, and they will either stay a sinusoid, and then sometimes they don't stay sinusoids. So what we are going to try and do is see, are they going to be sinusoids or not, and how can I tell the difference? Okay. So if we're looking at these two functions, and again, I have them graphed out so that we can take a look. So here's our first one. We had sine of x minus 3 cosine of x. So we put them together, we graphed it out. And if I were to look at this, I would say, yes, this is a sinusoid. It has a constant amplitude. It has a repeated pattern. And so, yes, I can say it follows that sine or cosine graph when I add them together. Okay. Now to take a look at the next one, same thing. So yes, this is a sinusoid because, again, it looks like a sine or a cosine graph. More than the fact that it just has a repeated pattern, that would be periodic. It has to resemble a sine or a cosine curve in order to be a sinusoid. So the big thing to take note of is if I were to say to you, well, if I analyze these individually, what's the period? So, sorry about that, wrong one. What's the period? The b value. So the b value is 1 for the sine curve. The b value is 1 for the cosine curve, meaning they would have the same period. Okay, if we look over an example 4, the b value is pi for both. So what does that mean? They have the same period. So sums and differences of sinusoids with the same period will be sinusoids again. So really what we're trying to do is when I take a look at the ones we add, what's the b value? If it's the same, you get a sinusoid. If it's not a sinusoid. So if we take a look at this one in number 5, I could look at it and say, okay, identify the b value. B value is the number in front of the x. And on both of those, I could say the b value is 1. So if I were to think of the period for the cosine function, I could tell you that the period would be 2 pi over b, or just 2 pi. Okay. Same thing for the period for just that sine function. Again, that's just going to be 2 pi over b, and since b is 1, it's 2 pi. Since they are the same, I can say yes, that has to be a sinusoid. Okay. Whereas if we look at letter B, okay, so the period for this cosine would be 2 pi over 5. And the period for this sine graph would be 2 pi over 3. So they have different periods. If they have different periods, then it's not going to be a sinusoid. Okay. So moving on. So we're going to take a look at this graph, and it says, okay, from what we just talked about, we should be able to figure out that it's a sinusoid. B values are the same, so that's great. So what we want to do is say, all right, if it is a sinusoid, what would that function look like? Meaning, how could I write that function so it's only sine or only cosine? Okay, so the first thing that we want to do is find the period of that function. All right, so the period of that function, well, since they both have a b value of 1, I can tell you the period is 2 pi over the b value, or I can tell you the period is 2 pi. Now, for right now, it says we're going to estimate the amplitude and the phase shift graphically using our calculator to the nearest hundredth. So if we were to take a look at this function, if I want to find the amplitude, I'm finding the maximum value of that curve. And now keep in mind your maximum value, we're looking for the y value. So I can tell you the maximum value of this is going to be at 5.39, meaning that's our amplitude. That's going to be your a value. And then we need to find the phase shift. Now, you can do a phase shift a whole bunch of different ways. I just try and find the one that's closest to the x-axis, the origin. I have chosen this one at negative 1.19, finding the 0. But I could have also chosen this one. This would have been fine too. This would have, if I'm thinking of my sine curve goes up, down, and comes back around. This would have been like, say, the start of a next cycle of the sine curve. Okay, I also could have taken this location because, again, sine curve starts at 0, goes up. That would have been another start of the sine curve. So you have a whole bunch of different options that you could have taken. Okay, so we found the amplitude. That was your max value. The amplitude turned out to be roughly 5.39. And we found that phase shift to be about negative 1.19. So when we write this function, going back down here, we're going to use this formula. Okay, that's our sinusoid formula. Our a value is that 5.39 sine parentheses our b value. Now keep in mind our b value we found back up here, and we said that the b value was 1 times x minus our h value. So our h value was negative 1.19, so there's plus 1.19, which hopefully that makes sense because we said it looked like it was shifted left, and if we do a shift left, it should be positive in our function. Okay, so I should be able to go back and take that graph, and I should be able to plot it. And if I type this in, we have about 5.39. We have sine of x plus 1.19, and when I graph that out, I can see that it's approximately that same graph. Okay. So our next one we have here, it says the function is periodic but not a sinusoid, and it wants us to find the period graphically. Okay, so again, we're going to go back to the calculator. I have this all graphed out. So I have it graphed out in the window from negative 2 pi to positive 2 pi. And it says it is periodic but not a sinusoid. So periodic meaning, again, it has a constant repeated pattern, and I can see the repeated pattern. Not a sinusoid because it doesn't look like a sine or a cosine graph. So they want us to find it graphically. In other words, take a look at the graph and see how long it takes for the function to actually repeat itself. And since the window that I have is from negative 2 pi to positive 2 pi, and I can see this happening twice, that means I have one period going from negative all the way up to 0. And then I have a second period. So I'm seeing 2 cycles of this graph, meaning this here from 0 to 2 pi is 1 period. From 0 to negative 2 pi is 1 period. So if I'm looking at this, I could say the period of this graph has to be a value of 2 pi. The last thing that we're going to take a look at is something called damped oscillation. And this picture that we have down below, this is showing you what looks like a sine or a cosine curve, but looks like it's squeezed. Okay, it's squeezed at 0. And taking a look at basically what happens when we consider a trig graph, but graphed with something else where it has some sort of a function being multiplied. So like, for instance, there in front of it or behind it. It looks like what happens is our wave becomes squished, okay, or squeezed. And we can see at this point it's being squeezed towards the origin. Depending on what happens, what factor you have, will depend on where that squeezing is happening. Okay, so what we get when we get that squeeze is something called damped oscillation. The factor, what it's being multiplied by, is the damping factor. And then we can see where it's happening, how it's taking place. Okay, so if we look at these graphs, so for this first one, I can see that this graph looks like it's being squished. And now it's being squished, but not towards the origin, but towards the right-hand side of my graph, whereas x goes to infinity. So I would say yes, this does have damped oscillation. Okay. The factor, so the factor is what it's being multiplied by. So I can say your factor is going to be 2 to the negative x. And I can also tell you that it's going to happen. So the damping happens as x is going towards 0. So kind of like when we dealt with limits, I want to know which direction it's happening in. Okay, and if I go back and I add that graph in, we can see, we said the damping factor was 2 to the negative x. And watch what happens. I can see it's getting squished. But now also notice that it happens on the bottom. So that would be like a reflection of that factor. So how about negative 2 to the negative x? And I can see that factor. Okay. Next picture we have, there's nothing happening. That's just a basic trig graph. It has no damping whatsoever, so no damping factor, no damped oscillation. And our last one, again, it does get squished towards the origin. It does have damped oscillation. So I could say, okay, so we said none here, but yes, this one does have damped oscillation. So our factor comes from what we're multiplying our trig graph by, which our factor now becomes negative 2x. And now this time, the damping occurs as x is approaching 0. And it approaches this from both sides. So you want to think about that. So it's approaching 0 from both directions. And if we go back and we graph it, remember we said we'd take that factor, so negative 2x. So if I try and graph that here, and I take negative 2x, I can see that graph, it's approaching 0. And now we said if I did a reflection of that, so a negative, negative, well, that would become a positive 2x. And if I were to graph that, I can see again, it's leaning towards those. It almost treats it like asymptotes as it's trying to reach towards the center. Okay. So that was a little bit of what happens when we combine trig graphs and we play around with them, noticing sinusoid, periodicity, those are going to be some big words, damped oscillation, and we'll practice some more of this in class. Don't forget to like and subscribe and have a great day.